Let's go. So, welcome to the first DaSCI seminar on this new academic year that will focus on coevolutionary problem solving. First of all, I want to thank Professor Xin Yao for very kindly accepting our invitation. Xin Yao is a chair professor of computer science at the Southern University of Science and Technology, Shenzhen, China, and a part-time professor of computer science at the University of Birmingham, UK. He served as the president of the IEEE Computational Intelligence Society and was editor-in-chief of IEEE Transactions on Evolutionary Computation until 2008. And his major research interests include evolutionary computation, ensemble learning, and their applications to software engineering. Among many other awards and recognitions for his excellent research work, we could mention the 2010, 16, and 17 IEEE Transactions on Evolutionary Computation Outstanding Paper Awards, 2011 IEEE Transactions on Neural Networks Outstanding Paper Award, Royal Society Wolfson Research Merit Award in 2012, the IEEE Computational Intelligence Society Evolutionary Computation Pioneer Award in 2013, and the 2020 IEEE Frank Rosenblatt Award. In today's seminar, Professor Xin Yao will present some applications of coevolution in learning and optimization scenarios, from situations when non-training data are available to large-scale global optimization problems in black box settings, and in the automatic design of general solvers for hard combinatorial optimization problems. So again, Professor Xin Yao, thank you very much for accepting our invitation. And whenever you're ready, the floor is yours.
Thank you.
Sorry, Xin, I think one person has opened the microphone.
Yeah, I think that's true.
There is one person. Probably you can close it because you are the owner of the session, Pablo.
There is a bit of a background.
Now it is okay. Sorry, you can start.
Okay. Yeah, thank you very much again, Pablo. Thank you, Paco, for attending this seminar in your busy schedule. I'm very pleased and honored to present some of my recent work on coevolutionary problem solving. So for an overview of the talk, it looks very long, but I'll spend most of my time on the introduction and an early example, really try to motivate why coevolutionary algorithms and coevolutionary learning is an interesting topic for research, and there's a lot of potential for further research as well. In order to illustrate that, and then I'm going to give you some examples of using coevolution for optimization. I'm going to give you some examples of using coevolution as a generic problem-solving approach. This is actually the title of my talk. First, introduction. The introduction, I would like to remind myself, coevolution is actually a very old research topic in evolutionary computation. I listed two references here, one dated back in 1987, where Robert Axelrod using genetic algorithm to evolve game playing strategies automatically. The other very seminal work is Daniel Hillis' work using coevolution in designing a sorting network automatically. So these two papers are very, very influential in late 80s and early 90s. I actually will claim that coevolution was made popular in those days by Robert Axelrod's work. Interesting, Robert is actually a social scientist rather than a computer scientist. It has always been an integral, a very interesting part of evolutionary computation. Although coevolution has never been the most popular topic, every now and then, this topic of coevolution pops up in journals and conferences But personally, I like this topic very much. I'll explain why I enjoy co-evolutionary computation very much. Before I move on, you probably ask the question, what is co-evolution? I heard of genetic algorithms. I heard of evolutionary algorithms. What is co-evolution? Conceptually, it's very simple. Co-evolution occurs when the fitness of one individual depends on other individuals in the same or a different population. So if you are familiar with a genetic algorithm, you know, in order for the evolutionary algorithm and genetic algorithm to run, we need to evaluate the fitness of individuals in a population. If this fitness is defined not only by this particular individual, but also by other individuals, then this is co-evolution. That means we don't have a fixed fitness for one individual. The fitness of one individual depends what other individuals in the same population or in a different population. If we look from the algorithm's point of view, this is a very simple co-evolutionary algorithm. The only difference between this co-evolutionary algorithm and a normal evolutionary algorithm is in step number 2, where we evaluate the fitness of one individual through interactions between this individual and other individuals in the population. So you can see one of the characteristics of co-evolution is the fitness is always relative, it's not absolute. Okay, given that very short introduction, I'm going to show you a very early example of co-evolutionary learning. Okay, so this is actually in the late 80s. Let's imagine a very challenging situation in strategy learning. We want to learn the best game playing strategy. Let's say this game is a very simple game we call iterated prisoner dilemma game. If you think of a very complex game, it could be a Go or chess. It's also a game. So you can imagine we're going to learn the best game playing strategy against a known opponent. I never met this opponent, but I want to learn the best strategy. So why this situation is challenging? Because in this scenario, we don't have any training data about the previous games played. Interesting learning problem, no training data. We don't have any teacher information guiding us what to do. Well, so there's no labels. Talking about the game playing, we are not even told whether a choice made in the game, in the learning process, whether it's correct or not. There's no such feedback information available to us. So now you can appreciate this is actually quite challenging learning situation because there's no training data. So all these great ideas about deep learning cannot be used directly. There's no training data. There's no teacher information to tell us what's right, what's wrong. Okay, that's a bit tough. For game playing, when we make a move, there's no feedback information to say whether that particular move is correct or not. If you think this is not challenging enough, imagine a slightly different situation. Suppose I'm a professor in a university. Just imagine a situation we try to teach a class of students, but I'm not going to give them any lectures, no lectures. I'm not going to mark any of their assignments and exam papers. So I'm not going to tell them what answers are correct, what answer is wrong. Now, I said, whether it's possible to learn in this situation? Right? Most people's first reaction says, well, how on earth is it possible to learn? You need to teach me. Otherwise, how can I learn? Okay. So here's evolution or co-evolution comes into the picture. Well, when we are facing a very challenging situation, why don't we give co-evolution a try? When you say, how does it work? Does it really work? Let me tell you the conclusion first. If we use the co-evolutionary algorithm I just mentioned to you a few minutes ago, you can actually discover the optimal strategy. Okay, so if we use this particular co-evolutionary algorithm, it's very simple. In the second step, when you try to evaluate the fitness of one strategy, all we need to do is to play this strategy against other strategies in the population. And then you get a score by playing. You get a score, but you don't know which one or which step is correct or which step is wrong. You actually do not know at the end of the game who actually got the correct ones, who's got the wrong ones. Okay, you only get the score. And then you use this co-evolutionary algorithm applied to the scenario of game playing strategy. With no training data, no teacher information, then you can actually learn optimal strategies. If you think of the example I said in terms of teaching students, which implies in theory, the professors can be very relaxed because you don't need to go to lectures to give lessons. You don't need to mark assignments. All the students need to do is to compare their answers with each other, and then come up with a relative score. And that's it. And then if you do this iteratively, you will be able to learn. So on the left-hand side of this slide, the x-axis indicates the number of generations for the co-evolutionary algorithm I use. A y-axis indicates the fitness, which is actually the payoff of the individuals. So that's somewhat surprising because there's so little information we have, yet we are able to learn the optimal strategy. So if we use the modern day terminology to describe that scenario, this is actually zero knowledge learning with no training data. So when alpha 0 comes into the world, lots of people say, hey, we have a zero knowledge learning with no training data. It's a great breakthrough. What conceptually co-evolution research was actually back down in early 90s. In any case, this initial success of co-evolutionary learning of game playing strategies has led to some optimism. In the 90s, there was actually quite a bit of research on co-evolution, including people from other domains. For example, people in business studies has taken the approach very seriously, try to use co-evolution approach to evolve business strategies. They call it breeding competitive strategies. And some people use this to explain strategies in the defense sector. However, after several years research, people discover, apart from some very interesting applications, especially in game playing strategy learning, there are still some research questions remain open. For example, there's issues related to robustness of co-evolutionary learning. There's an issue related to cycles. There's an issue related to mediocre stable states. If you are not familiar with terminology, it doesn't really matter because the message you want to get through is in terms of fundamental research, people discovered co-evolution might not work as an ideal approach in discover optimal strategy. Sometimes it works, sometimes it doesn't, and people does not know in theory when it works. Because of this, as a human nature, some people dismiss co-evolution very quickly. They tried the co-evolutionary algorithm, it did not work, they just claim, oh, co-evolution does not work. In this situation, as you know, in university, we are under a lot of pressure, especially for some students. They are looking for more productive research topic to work on so they can publish. So in those situations, people discovered all these low-hanging fruits were picked, and then all the remaining research topics with the co-evolution becomes very hard. Around the same time, more interesting topics emerged in evolutionary computation, such as particle swarm optimization appeared in 90s, and then differential evolution occurs in 90s as well. They show a very promising result in global optimization without using any derivatives. Quite interesting in research, similar to other domains. If you keep working on some topic, you suddenly discover the weakness of that technique. So when people use PSO or DE for global optimization, they very quickly discover when the number of decision variable increases, when the problem scales up, all these PSO, DE, or other meta-heuristic algorithms did not actually work very well. And this is quite frustrating, especially for researchers like myself, or especially for my students as well. They thought they discovered a very interesting topic areas like a PSO. They publish one paper, and then they try to apply the method to a real-world large-scale problem and discovered actually PSO or DE did not work as well as we hoped. Then we are stuck somewhat because in my search for interesting research topic I can publish or I can make progress, I'm getting stuck. So that's the message of my talk. When everything else fails, please try co-evolution. You see, I'm trying very hard to sell the idea of co-evolution to you. Let me show you how co-evolution could actually help you or help us in tackling large-scale global optimization problems. Okay, let me describe the idea first, and then I'll show you some examples. So the particular types of co-evolution we are using is called the cooperative co-evolution for global optimization. The original idea can be traced back to 94. Mitchell Potter and Xin Yao published a paper at the PPSM 94 called a cooperative co-evolutionary approach to function optimization. It's very interesting. You probably noticed that all this interesting paper with original ideas occurred in 90s. So somehow 90s is a very good period for research ideas. Might not be very good decades for commercialization. Anyway, back to this topic in terms of cooperative co-evolution. When we apply cooperative co-evolution for global optimization, normally we have three major steps. One is for problem decomposition. Second step is for subcomponent optimization. Third one is subcomponent co-adaptation. Okay, so this is a very typical divide and conquer strategy. So you can imagine this co-evolution as an automatic approach to divide and conquer, because we divide a large problem into smaller subcomponents, and then we do subcomponent optimization, and then we put subcomponent solution together through co-adaptation, forming the solution to the original large problem. Okay, so very intuitive. But how do we do this? Right? It's very easy to say divide and conquer. How do we do the division? Here is the simplest idea first. If I have a large scale problem, high dimensional, okay, let's say is n dimensional. And then I can always decompose this n dimensional problem into m s dimensional problems. Okay, suppose I have, say, a 1,000 dimension problem. I can decompose into 10 100 dimension components. For 100 dimension, I think I have a good algorithm in solving them. So that's actually the intuition. I decompose 1,000 dimension optimization problem into 10 100 dimension optimization problem, as illustrated here. For 100 dimension, yeah, I think I have a satisfactory algorithm in solving. So this problem decomposition is basic idea. Once you have this basic idea, there are lots of problems that suddenly pop up. Okay, you want to decompose a 1,000 dimensional problem into 10 100 dimension problem. But out of this, which variables should be grouped together? We have 1,000 here, which 100 should be in a group? Which other 100 should be in a different group? What's the answer? Well, we don't really have an obvious answer unless we have additional information. Okay. If we don't have any domain information, well, what we can do is, why don't we do it at random? We really don't have any other choices because we don't have other domain knowledge. In other words, if I have an n-dimensional vector, I just split them purely at random. That means for every single variable, it has an equal probability to be put into any of the subcomponents. Okay, nothing very clever about it because I don't have any domain knowledge to be clever. So you probably wonder, say, what? How can you just do things at random? If you do it at random, how can it work? Let me tell you the conclusion first. Random grouping of variables, if we carry it out at every generation of an evolutionary algorithm, it does work. It works because if I do random grouping at every generation, we can do a very quick calculation to compute the probability of any two variables to be put in a group. And then you can actually see this probability is very high as the number of iterations goes on, which implies if I run this co-evolutionary algorithm with a random grouping, any two variables has a very high probability to be in a single group during this evolution. That means any correlations between these two variables can be captured at least once. So this actually does work. It's not very clever, but it does work if you do random grouping at every generation. The price I paid is extra computation time when I do the random grouping. Well, although it's not very time consuming, it's still a bit of overhead. I'll skip the result. The result, actually, the two slides really demonstrate that if you run the experiments, you can do the comparison, and then the comparison actually shows the idea works. So this idea, you can imagine, it worked well for all the separable problems. it worked well for some non-separable problems, but for some other non-separable problems, it did not work very well because it's random grouping. If we follow this direction of thinking, it's not too difficult to think of better grouping schemes. This differential grouping basically is a method trying to discover interdependencies between variables such that we can put variables with strong interdependencies in the same group, and we put variables with very weak or no interdependencies into different groups. Okay, this is we come up with a name, differentiable. Differential grouping doesn't mean we use derivatives. We don't use any derivatives. We just call it differential grouping. So the core idea is to identify variable interactions. We can put strongly interacted variables into one group, and then weakly interacted or no interaction among variables into different groups. One of the side benefits of doing this is now I can do decomposition where the group sizes are different, because some of the groups might be larger, some of the group might be smaller. So the group size is actually determined by this differential grouping method automatically. So after we proposed this method back in 2014, there are a lot of further improvements on differential grouping. Actually, the latest work of differential grouping was published this year by a group in the US. Try to increase the efficiency of differential grouping. So even among my own group, and then we have increased the effectiveness of differential grouping by considering if we have a problem decomposition, we decompose problem into different components. Some components actually contribute to the global optimization more than others. Then we can make use of this contribution in computational resource allocation in order to speed up the convergence of the algorithm. And then we can use this recursive differential grouping to increase the efficiency of the differential grouping method as well. Finally, I want to mention that there is a public domain toolbox actually in MATLAB. If anyone is interested, you can just download it. It is freely available in public domain. Okay. So far, I mentioned this automatic decomposition, we call it grouping. But co-adaptation is also very important, because when we divide a large problem into smaller pieces, okay, how to do the division is important, but we need to ensure we eventually will solve the larger problem rather than just the components themselves. And then the co-adaptation among different components or different groups is actually done through fitness evaluation. Let me show you this diagram in terms of co-evolutionary algorithm. Within this diagram, I have an artificial example. Suppose I have a so-called large problem with 6 variables. And then I decompose this larger problem into 3 smaller ones, or 3 components, group 1, group 2, and group 3. Each group, I have a subpopulation. I can use evolutionary algorithm to solve it. However, when I try to evaluate the fitness of an individual in group 1, for example, I only have information about X1 and X2. I don't have information from X3 to X6 because the problem has been decomposed. I'm only looking at the evolution of two variables, which are x1, x2 in group 1. So in order to evaluate the fitness of individual, I need to communicate with group 2 and group 3 such that I can get the value of x3, x4, x5, and x6. So this communication really slowed down the co-evolutionary algorithm. If we are thinking about the parallel processing, it's actually the communication overhead. So the small challenge we have here is anything we can do to reduce the communication among different groups, such that we can increase the efficiency of the entire co-evolutionary process. So the idea here is kind of straightforward. We called it self-evaluated evolution. Okay, let's look at this diagram at the bottom of this slide first. On the left-hand side, this is classical CC, means cooperative co-evolution work. And in the middle part, partial, means one of the many decomposed groups. In order to evaluate this orange individual in the middle, we need to borrow the variable values from left and from right. That means I need to get variable values from other groups such that I can get the fitness. And this process is time consuming. On the right-hand side of this bottom is our SEE proposal. So our cooperative co-evolution idea basically says, is there any way I can come up with a meta model we call the R? It's very important to remember this meta model, or sometimes we could call it the surrogate model, is not used to approximate fitness. We do not approximate fitness using this meta model. Instead, we want to build a meta model to approximate the selection process directly. If we can learn this model, then given this partial individual in the middle, then we can use this meta model to say whether we should retain this in the next generation or whether we should actually throw it away for the evolutionary process. Okay, so conceptually, it's a very simple idea. Is instead of trying to approximate the fitness function, we try to approximate the selection process, such that we can reduce the communication with other populations or other groups. And we call this self-evaluation evolution, because I don't need keep asking others for variables. Interestingly, this method not only can give us better results, it also have a better scalability. So this diagram actually shows we tested on different benchmark functions. Each figure, each sub-figure is on one benchmark functions. X-axis is not generation number, by the way. X-axis is the dimensionality of the problem. You can see we tried the problem of 1,000 real valued variables up to 5,000. So for evolutionary optimization is quite large problem, right? It's a 5,000 real valued variables, 5,000 dimension vectors. If you look at this red line, it's always the lowest. It also grows the slowest. That means the y-axis indicates the quality of the optimization. We are doing minimization here, so the smaller value will be better. Okay. There are a lot of other work by other people, of course, on this large-scale global optimization. I won't be able to go through all of them here. So now I'm going to describe some real-world problems. So previous work is done on benchmark functions. People are really finding quite boring. Okay. So without going into nitty-gritties of all applications, I'm going to mention the 4 problems to you, which has been solved very effectively through coevolution. The very first example is shape optimization. So the particular collaboration we have with the Honda is in optimizing the shape of turbine blade. So in this particular case, we have a 2 population coevolution. One population contains control points of the B-splines, indicating the shape, and a different population contains knot vectors. So if you do a computational comparison, it's actually outperformed all the other single population evolutionary approach or alternative approach. The second example is in concurrent engineering. So this is actually very traditional engineering domain where concurrent engineering consider all parts or all aspects of the product design simultaneously. The objective is to discover any potential errors earlier in order to avoid costly redesign. As you can imagine, if we consider all parts or all aspects of product design simultaneously, we get a huge number of design variables. It's very complex. There are lots of design variables. So traditionally, people use so-called multidisciplinary design optimization approach. And then you may have one discipline focusing on safety, one discipline focusing on aesthetics, the other sort of a discipline focusing on, I don't know, air resistance, etc. So the approach we come up with basically says, actually, I can imagine each discipline as one subpopulation in a co-evolutionary design process. Okay, so this is actually a diagram. If we take that particular point of view, then this is quite similar to cooperative co-evolution for large-scale global optimization. In this particular case, we do not need to do proper decomposition because each subproblem is actually one discipline. So from algorithm's point of view, there are similarities between concurrent engineering and large-scale global optimization I just mentioned. And then we actually applied it to some real product design, and then did a lot of computational comparisons and illustrate co-evolutionary approach does offer some advantages. The third real-world example is actually in VLSI design, especially in design space exploration. So conceptually, if we have a multi-core machine, on the left-hand side, suppose we have a number of task graphs. And then this task graph have different modes. Then we want to execute all these tasks on parallel processes. On the right-hand side, we have a P0, P1, P2, etc. So these are processes. And then the objectives here is to minimize some kind of make span. It's actually minimize the idle time for the processes. How do we do this multi-mode task graph assignment? Traditionally, the state of art is on the left. It is actually based on a genetic algorithm. A lot of people say the genetic algorithm is very slow, but sometimes for some applications, the best state-of-art algorithm, it is actually a genetic algorithm. So this is actually on the left. Because we are facing this multi-mode task graphs. So very intuitive extension of this work is to use coevolution. If we use coevolution, we have subpopulations. Each subpopulation, we focus on one mode only. So instead of have one giant chromosome, we have multiple smaller chromosomes. So it actually shows here. Okay. So instead of just one population, for this diagram, we have a multiple subpopulation. They are co-evolving each other. So if you compare this co-evolution approach with this state-of-the-art approach, the efficiency has increased significantly. Interestingly, not only can we increase the efficiency, we actually increase the quality of the solution as well. So this is actually the benefits. So I will skip this actual result. And then the last example I want to show is using coevolution for capacitated arc routing problem. So capacitated arc routing problem is a very hard combinatorial optimization problem. Basically says, given a graph, given a fleet of trucks, how do you dispatch and schedule these trucks going through routes within this group and then service the required edges? So this is actually the idea we come up with. Instead of using one evolutionary algorithm where the chromosome has to contain a set of routes. The reason we need a set of routes because each truck needs a different route. If a 10 truck, we need 10 routes. When we introduce co-evolution, basically each individual, or not each individual, each subpopulation, you only look at a cluster of routes instead of all the routes. And then when you put all the subpopulations together, that actually will form a whole set of routes. And this decomposition actually speed up the evolutionary process. Interesting, as I mentioned, in this case, can also help find better solutions. Okay. Now I want to come to the very last bit of my talk. And here's the connecting slide. I show you why this is some interesting work I'm doing at the moment. If we are thinking about the combinatorial optimization problems, every variant of a problem, if you're adding a new constraint, and then normally you require a new algorithm. For example, in this cup, if I adding in new objectives like a total service time and the investment cost, in addition to the route length traveled, then we have to come up with additional algorithm. We cannot use the previous algorithm. If we come up with additional objectives, we have to update our algorithm because single objective algorithm cannot be easily reused for multiple objectives. If I change the map from single depot into multiple depot, then I have to change the algorithm. If we introduce uncertainty in the map or in the trucks, I need to design algorithms. So designing algorithms can be interesting sometimes, but can be quite boring. So it's very time consuming to actually design good algorithm. But sometimes I always have a joke with my students. It's very bad, very boring to design good algorithm, but it's good for you to write papers because if you design good algorithm, you write one good papers. Okay, so a real interesting question is if designing algorithm becomes a bit tiring and boring, is it possible to design algorithms automatically? Well, some of you would say, no, algorithm design has to be the job of computer scientists. Some of you might say, well, actually, it is possible to design algorithms automatically because for some computer scientists, in principle, you can design anything automatically given some conditions. Okay, so optimistically, we know we can tune algorithm parameters automatically. Now there is a subfield in machine learning called auto ML. Well, auto ML is such a beautiful name, but in essence, it's just parameter tuning. So I sometimes very angry people in machine learning. They always come up with this beautiful name to describe something which seems to be relatively common. Anyway, back to my topic. If we can define algorithm configuration space, then in principle, we indeed can design an algorithm automatically, because if I have a formal space I can search, I should be able to do it automatically. Okay, that's the title of my talk. I want to use coevolution as a problem-solving approach. Okay, I don't want to design algorithm anymore. All I need is coevolution. So here's the first slide to show. In the middle, I have this orange algorithm. At the present, this algorithm is designed by me. I designed this algorithm to solve a problem called F. Now I'm getting old. I'm unable to design a good algorithm. Then I say, I'm going to design an algorithm configuration space for this orange one. And then I design an outer loop evolutionary algorithm to search within this algorithmic configuration space. So I use this outer loop EA, evolutionary algorithm, to design this orange algorithm. And this orange algorithm, once it's designed, it is used to solve the problem F. Then you might ask, can you do that? Of course I can do that, as long as I can come up with a configuration space for this orange EA. Then I can use this outer loop green EA to search for it. Evolutionary algorithm does not require any gradient information. It can be applied to a combinatorial space or any discrete space. Very good. At least I'm moving towards being lazy. One step closer. I can design my targeted EA automatically. Then you probably ask the question, that might not work, because if you use this diagram to design your orange EA, that orange EA can only solve this kind of a blue F problem. So it's kind of overfit to problem F. If you find a good algorithm for problem F, what if you have a different problem called F prime? Would this targeted EA still be any good? So this is a little bit analogous to generalization issue in machine learning, okay? Not exactly the same. But this is very annoying to me because I want to be lazy. I don't want to design algorithm. I thought I'd discovered a fantastic approach being lazy, evolving an algorithm to solve a problem. Now someone come up with this overfit problem, ask me. I don't really have a fixed answer. But I remember one of the things in my mind, when everything else fails, I can try coevolution. So here's a very interesting coevolution idea. So probably the second to last slide I'm going to show. So the slide really just says, okay, previously I have this orange EA to solve problem F, and then I introduce this outer loop EA to search in the configuration space of orange EA. Then someone challenged me saying, if you evolve this EA is only good for this blue problem F. Now I say, okay, I'm going to introduce another population of problems. So this purple one is a population of problems. So now I have a coevolutionary algorithm. On the left-hand side, I have a population of possible algorithms. On the right-hand side, I have a population of challenging problems. On the left-hand side, the algorithms try to solve all the challenging problems in the right population. For the population of problems on the right, it tries to evolve even more challenging problems which cannot be solved by any of the algorithms on the left. So this is actually back to the classical arms race of competitive coevolution. Then you say, well, the story, of course, you can say this. Does this story actually work in practice? Let me show you one case study. I take this idea I just mentioned, and then I use one real-world example as my original problem, like this blue F, to initiate the population of problems. And then I use this co-evolutionary method I just described to you to evolve a solver for solving vehicle routing problem. Okay, I built this solver, it's evolved. After I evolve this solver, keep in mind this solver basically is a vehicle routing algorithm. And then I apply this solver without any changes to a set of benchmark problems. And this set of benchmark problems has never been seen, has never been used in this evolutionary process. Surprisingly, this evolved algorithm, not human designed, actually outperforms other state-of-the-art algorithms. Not only outperformed some other state-of-the-art algorithms, for some of the benchmark problems, we discovered the best results so far. That's a bit interesting. We need to keep in mind that evolved solver has not been changed. We apply to a different problem. Okay, so this actually illustrates this co-evolutionary problem-solving approach where we have a population of potential algorithms and then we have a population of potential challenging problems. It's actually a very interesting problem-solving approach because in this particular framework, I never say what kind of algorithm they should be, what kind of problem they must be. Okay. So I need to skip some of this theoretical result and then move to conclusion part so we have some time to discuss. So I hope my last bit somehow convince you a little that co-evolution could be used as a problem-solving algorithm. But actually, you can also see co-evolution as a problem-solving strategy, okay, as approach. It is a very old idea. It is very simple because in the introduction slides describing the basic idea of co-evolution is just one slide. And I show you it can be used as an algorithm to solve some hard problems, especially when other alternatives fail, which basically means that if you don't have a lot of domain knowledge you can use, maybe co-evolution could be a good alternative for us to investigate. But I have to admit that I present a lot of work which I'm familiar with. Co-evolution is actually much broader than what I just mentioned. Last bit I want to mention that I want to encourage more younger people to get into this research area. I think there are a lot of research questions have not been answered. which implies there are lots of opportunities for doing some interesting work. I will stop my talk here, and then if you have any questions or if you have any comments, then I'll be very happy to take them.
Well, thank you very much for this very nice talk. So now it's time for questions from the audience. Well, feel free to write directly the question in the chat, or just write your name, or so I can give you the turn to speak, or whatever you want.
And Pablo?
Yeah, go ahead, Paco. Yeah, sure.
Well, thank you very much by your very interesting work. Really, we have used several times coevolution for different problems, basically in the decomposition of with different representation in machine learning. For example, putting together future selection and instant selection as two parts of the chromosome, really two sub-problems evolving to have a global solution. Now, one of our PhD students is here, Javier Poyato, we are working on the evolution of deep learning, and we have been trying to use coevolutionary algorithms with we have in mind to code one chromosome is called the lax layers of the neural networks, and we tried to code in other chromosome some parts of the coevolutionary neural network, some kind of elements, some kind of operation, but until now was not possible to advance, because really the problem is the high time consuming. You have said in your presentation, really in large scale problem, particularly deep learning is really a high consuming problem. Really, if we need to train one model for each chromosome or each set of chromosomes, really is terrible the time. We know that Google is doing that, but of course the hardware of Google is not limited, but near. In our case, we are working with a class GPU workstation, A800 model, but really we have limitation. Do you have experience trying to apply the coevolutionary to this kind of really so high consuming time?
So we are aware both Google and Facebook, they actually use the co-evolution, although they only called it the evolutionary algorithm. But if you look at detail, they use co-evolution scheme. When we read their papers, we found it's very difficult for us to follow their work, because they really use a lot of GPUs running for 2 weeks. It's very hard for university people to compete. So what we said is, in terms of co-evolution plus deep learning, it's not possible to do the type of research Google and Facebook are doing. What we try to explore, one thing was a slightly different research issue, because we consider if we want to have one neural network to perform different tasks, okay, instead of just one recognition task or one, I don't know, speech recognition task. We investigate the so-called issue of modularity in neural networks. And then we try to answer a research question: why in most of the neural networks for a single task, you don't see the modularity, but when you have one neural network enforce them to learn multiple tasks, you can see some kind of modularity emerging. If you can see that, and then there is opportunity for co-evolution to play, because our plan is if we want one neural network to do multiple things, these multiple learning tasks can be organized in a co-evolutionary framework. So that's one of the research we're actually planning now. We haven't actually got any result. So I'm just sharing with you in terms of co-evolution and neural network. Actually, that's the work we are currently doing. Not really the way Google and Facebook are doing. They are very resource hungry in that work.
Yes, you are right. Really, they have really a lot of GPU, a long time for experiment. This is a problem. We have probably just this kind of multitask and decomposition, probably sequential.
Yeah.
In sometimes to use part of the convolution, perhaps at the end of the process, but we need to think probably the combination of different kind of decomposition alternatives.
That's right. Yeah.
Yes, you're right. Thank you very much. Thanks.
Yeah. Thank you. Thank you for your question.
So now, Carlos Núñez Molina, please go ahead whenever you want.
Okay. So, can you hear me?
Yes.
Okay.
Yeah, sure.
Okay,
Perfectly.
yeah. So first of all, thank you very much for the presentation. So I had two questions. The first one is, when you talk about the divide and conquer algorithm, you say like the main idea is to evolve each subpopulation separately, but there is still some communication between the different subpopulations. So what are these communications? So like, for example, do you need to communicate? I think you mentioned when you had to evaluate the fitness of some partial function, but maybe with the self-evaluation is not necessary anymore. And the second question was, so I think the most mainstream application of convolution is maybe in the form of GANs, of generative adversarial networks, but it seems to like there are a lot of issues with coevolution at least in that regard. For example, things like mode collapse, like you can have GANs that are very difficult to train and sometimes they don't converge to this Nash equilibrium. And for example, I think that's one of the reasons why diffusion models have got so popular in recent years. So what are your thoughts about the stability of coevolution? Are these algorithms stable, or sometimes they fail to converge or have some problems like that? Thank you.
Okay, I think those are very interesting questions. The first one, in terms of communication, is indicate this situation. I think your understanding is correct. If I have a co-evolution of 3 subpopulations, I call the 3 groups here. And then for group 1, I'm only evolving x1 and x2. But I do have a larger problem with the 6 dimensions. So in order to get the fitness of one individual, I need to know the value of x3 to x6. But x3 to x4 is actually in group 2, x5 and x6 in group 3. So whenever I do a fitness evaluation, I need to communicate with the group 2 and group 3 to ask these groups to pass these variable values to me. Okay, and then which variable value should be passed, and then that's actually different among different co-evolution algorithms. Sometimes you pass the best value to other groups. Sometimes you actually pass the first few best values as average to that. Okay, so that's related to your first question. This is what I referred to as communication overhead. Because if I'm thinking from parallel processing point of view, this is actually things which will slow down the parallel processing. In terms of your second question, co-evolution does suffer some of the problems you mentioned, although the terminology might not be the same. Let me just go back. So in early days, in 90s, people realized co-evolved strategies or co-evolved machine learning models might not be robust. Okay, so there's a robustness issue. There's an issue in terms of cycles. That means co-evolutionary algorithms never converge. Okay, they go in cycles. To make things worse, co-evolutionary algorithms can stuck at a mediocre stable state. And this is not local optimal. It's just a poor result. It's a bit like, I don't know how to say that. It's a bit like two friends who decided not to complete any homework. They are equally good. Actually, they are equally bad. Okay. So co-evolution is a bit like sometimes you can get stuck. You hope one will be better and the other will learn, try to be even better than the other one. But you can get into the situation, these two people decide to do nothing. Okay, so a co-evolutionary process actually stalled. I have not investigated GAN in depth, but I have a strong suspicion there are similar behaviors with GAN. I always tell my students, one of the very interesting research topic is try to explore deeper links between co-evolution idea and GAN. Because they does sound somewhat similar, but they're not exactly the same. And then we accumulated quite a lot of knowledge in co-evolution over the last 20 years. Maybe there are some knowledge transfer someone can do. I think it will be very interesting. Either ways, some of the knowledge could be transferred from co-evolution to GAN. Maybe you can discover new behavior of GAN inspired by co-evolution or vice versa. I have not explored myself, but what you said, I think it's a right observation. Co-evolution does not always converge.
Okay, thank you very much.
Yeah, thank you.
Now, Oscar Cordon. Oscar, please, whenever you want.
You listen to me?
Yes.
Hi, thank you. So it's so nice to attend to your talk. Thank you so much, and it's always a pleasure. So actually, my question is almost answered because I was also focused on the competitive coevolution. So I was going to ask you about that. Mainly, all the research you have presented that is very extensive and it's so interesting was focused on cooperative coevolution, and I wanted to know your view on competitive coevolution. And actually, I also thought as Carlos and you on GANs. So I like it so much when you mentioned about AlphaZero and about that was already invented on the field of cooperative coevolution. So to me, there is a strong synergy between GANs, generative adversarial networks, and what we studied at the beginning 20 years ago on, for example, the robotics applications on the coevolution of the environments and of the control rules for the robots. So at the end, it's a very similar task that the one that is done at the GANs. Yes. So I wanted to know your view, but mainly I'm a little bit late because you already mentioned that you also identified that similarity and you think it's an interesting topic. So.
Yeah, I always think that that's a very interesting research topic because people's intuition is saying, oh, that's actually similar, especially for people who did some co-evolution before. When they first saw GAN, they say, oh, that's quite similar. Even when some of us first see AlphaGo, and then AlphaZero especially, this self-play, they probably think of, oh, this is actually very similar to this TD lambda stuff, where you have one neural network, and then you mutate it, generate another neural network, and then you play against each other, and they iterate it for millions, and then that's how you get this master level backgammon. Okay, so conceptually, you thought that there's a lot of similarity, but I don't think there are people writing papers to actually pin down where the similarities are, what are the key differences. So I always think that there's interesting research to be done there. Yeah.
Thank you so much.
So for the competitive co-evolution, the very last diagram, I put it back here. So this one is really competitive because one population of algorithms and then the other population problems. So in terms of idea, I think it's the same as Daniel Healy's idea. Daniel Healy's example, they don't have this target EA, and then he has a sorting network in here. In terms of population problems, Daniel Healy's has a lot of test cases. So you basically a lot of test cases compete against a population sorting networks. So I think I just take the idea a bit further and generalize it. It's somewhat surprising in terms of results we obtained. Yeah.
Okay, well, thank you very much. I think that with these questions we can close this session. Thank you very much, Professor Xin Yao, for this very interesting talk, and thank you to all the attendees and all the interesting questions. So
I'll thank Pablo for giving me this opportunity, at least to see some old friends, Oscar and Paco and some others. It's been a long time we haven't seen each other physically.
It's our pleasure.
We see people in 2D, but sometimes I want to see people in 3D.
Thank you very much. Really, it's a pleasure to meet online with you, and I hope to meet you soon in a conference. Thank you very much. And we will continue trying to work in the topic, and if we advance, it will be a pleasure to keep in you with you.
Yeah, absolutely. I would love to hear from you. Yeah.
Okay.
I'd love to hear from you. Yeah.
Thank you very much.
Okay, thank you.
Okay, thank you. So let's close here our session. Thank you very much.
Bye, Dave. Yeah.
Bye,
Bye,
bye.
bye.
Xin Chao.
Bye, bye.
Esperar un poquito el resto que quería comentar. So thank you very much, Xin Yao. We are going to explain some news about the